no. It is. Check your audio connection. Now.
This should be much better. Let me know if you are able to hear it. It's the same. right? Actually laying a foundation, and then these are essentially being used for data processing, and then these are optimized with the help of parallel processing, and then the applications of different kinds of AI, right? Of course, the mathematics is the essential basis of this, right? And then yeah, next slide, please. Okay, okay. Now getting to the meat of the subject on what exactly is this parallel computing. Uh, Now we can look at each and every domain. Each and every domain is getting more and more specialized, and the kind of problems that are being addressed is becoming more and more diverse. And then as it goes on, the complexity of problems are also seen to be increasing. So in order to overcome these problems, what we are trying to do is nothing but addressing the problem into more smaller chunk of problems, or addressing the problem and then quantifying it to define to execute in different parallel ways, right? Irrespective of whether it can be one singular system or it can be deployed in multiple systems, in a small network or across the globe or across the wide regions, right? So this is what is becoming very common, right? And this is what the parallel computing essentially meant for. So so what is happening on one of the question that comes is that how we are able to do this. So it's very much it's very underlying is nothing but the if you look at the CPU trends now, initially the number of cores on every year, if you look at how many number of cores are being present in a CPU, it's getting on increased, and then the capability of GPUs is also getting incremental, and then new terms and technologies are coming like TPUs and DPUs, and then it's not only the hardware side but also on the software aspect of it as well, right? For example, if you look at CUDA, which was initially being propagated by the NVIDIA, right? And OpenMP is just open standard that was for that was meant for getting to a common standard where multiple computers would be able to communicate, right? So all these things are becoming part and parcel of this cycle, and then of course there are new evolving frameworks and technologies that are also getting every day. And one aspect of this is nothing but, if you look, there is no one single vendor or anyone who is dominant enough. Much of the frameworks in place is all because of the open sources, and then it's a combination of both commercial and also open source frameworks. Okay, yeah, next slide, please. Need for, yeah, uh, yeah. Just to put it, the relevance of HPC in sciences, right? Of course, just to put, it's in drug designing, genome sequencing, protein folding. Uh, it's there in life sciences, nuclear sciences, and nanosciences, right? Next one, please. Any kind of engineering, any kind of technology, any kind of science, all these things have the relevance of the HPC. And then of course each and every company has a certain models, right? For example, if you look at some of the companies, just to put it across, up to most recent, up to let's say up to 2016 and 2017, most of the companies which were earlier used to have a core engineering products, and then which were built from 1980s, right? Especially when I speak of a one complete product, it is a combination of different systems, from communications to data storage, and then doing the process analytics, and of course control systems, so on and so forth. So all of them in one sense are leveraging the changes of the cloud systems, and also the new architecture in terms of the edge systems. And then the implication is that if you look at some of the companies like ABB, right, which was especially meant and initiated, which was there for the last 150 years on this, purely on the power, it has actually migrated, it has actually sold it off to some other company, because what they envisage and what they see and the amount of returns is something very different. For example, if you look at, if they have sold to Hitachi, which is a Japanese, right? Japanese are very happy to have 5 to 6% returns per year, right? But the future trends is building a digital set of products, And then when we say digital, the application of AI and ML, the same set of algorithms would also be applicable. The same set of neural computing would also be applicable to many of the problems. Of course, it needs to have the domain expertise, right? So, nevertheless, to say that, okay, now this whenever there is AI and ML involved, right, and then we require quite a good amount of HPCs, high power computings, and then they might actually build their own set of stacks on the on premises, or they might actually they might leverage the cloud, right? So previous slide, please. Previous slide, please. So whatever that we are seeing now in this slide is nothing but some of the aggregation, whereby what is the current state and whereby the technologies have matured, or realistically we can actually utilize them, right? And then what is going to happen on, right? If you look at artificial intelligence, machine learning, right? Nobody has envisaged that chat gpt or DeepSeek or Gemini, these are the things that would come into picture just before 2 to 3 years. They might have been in the research labs, but nobody has actually predicted it. But right now they are very much in the for the social, right, usage. And then of course if you look at healthcare, right, this AlphaFold in 2016. And of course, if you look from the last 20 years, there are many companies like Siemens which have actually delved into the medical imaging, and they're doing quite good, right? So if you look at once again with the transport systems, Tesla has come into the picture. And then if you look at each and every segment, there are quite a number of problems, and then there are also huge implications of AI and ML provided by that domain aspect. And then all this is possible because of the infrastructure that is available, and out of which computing is one of the essential things, right? And just to put an analogy, if you look into the current cloud systems, right, and then for computations it's relatively less, right? And then the charges that is being levied is less. And then quite amazingly, in the most recent DeepSeek, what are the kind of $600 billion it has impacted on the Nvidia. Uh, people were wondering what exactly is the DeepSeek and how it is relevant to the Nvidia. What DeepSeek has explained is nothing but they are actually they do not have this so much of computational capability, but they leverage the underlying principles in order to minimize the amount of computational needs, which is quite an innovative thought, right? And then these kind of I mean, it's not only purely technology but application of technology, right? In the way forward, we'll be able to see quite some scintillating amount of changes in each and every of these fields, and also on the computational capability, right, in most innovative ways. Yep. Next slide, please. Okay. Now, when we say of parallel computation, essentially what we are seeing nothing but large, yeah, communicating of large problems, and then they are subdivided into small problems, and maybe some of them can be executed in parallel. Yep. Next slide. Okay. Now these are the previous slide, please. This is a trend of the microprocessor over the last 45 years. This is actually inserted from the open source. Now, one of the questions if you see is that number of logical cores, as we see from the mid 2000s, we can see it to be increasing, right? And then typical power in terms of power watt consumption probably is more or less at the same, or it may be a bit less because the vapor scales are getting reduced and so on and so forth. And then the frequency is also more or less the same. But if you see at the single thread performance, right, the dots, if you see, it's actually more or less looked very stable from probably in the late 2020s, even though number of transistors are increasing, right? This is a bit perplexing, right? This is essentially because of the fact that the more number of pores are being used, it's creating a bottleneck, right? So this kind of technology, even though if we increase the wafer scales, which will help in terms of the optimization of the of the power consumption and so on and so forth, or miniaturization, but it's not going to help in terms of the single threaded performance at large, right? The computational capability would increase, but it will have a certain implications. Yep. Next slide, please. Yeah. Okay. Now, we just before we go further, there are a couple of terms I think we need to understand. What is a CPU, GPU, DPU, and TPU? CPU is something which is known, which is existent for quite some time. There is nothing much to delve into it, but what we can see is that nowadays the cores are from 2 to 64 cores, right? And then GPU is also there from the late 1990s, or of course much before. Essentially, it has been used more in terms of accelerating the graphics and from mid 90s or early 2000s, so on and so forth. It had gone into some prominence because of usage in the gaming devices, right? But it remains stagnant at that point of time, right? But unlike CPUs, a GPUs can have a 10,000 cores, and they can do amazing performance. But of the late shoot, if you, from 2016 onwards, whenever people nowadays we hear of TensorFlows, right? And then which is offshoot from the Google, essentially for the machine learning. So essentially, a TPU is nothing but tensor processing unit, and then this is initiated by the Google, and then from 2012, and then practically even they had released hardware chips inline to the TPU. We can see essentially from 256 to 1000 cores, which essentially meant that it can do matrix operations, 256 to 1000 parallel matrix operations. Now we can see one more as a DPU. This is something which is more like a CPU. It's more like a CPU, but it is meant for a very specific purpose. Now, one of the, for example, if I want to do a general purpose and the general purpose operations, and then I want to connect between servers, and then one of the essential things is nothing but whether the servers are trusted or not, whether the cryptographic keys are matching or not while sending the communications, whether I mean, instead of the CPUs or CPUs doing the specific operations of the cryptography and so on and so forth. So these DPUs are the specialized chips that aids in doing that, and this has come in more recently from 2018 onwards by the Intel and the AMD. So nowadays, these are the four essential processors that would aid us in terms of the computations. Now, if you look at onto the right side, what you can see is nothing but NVIDIA-based process. Which can scale up to 34. I mean, each one of them. If you look at tensor cores or normal GPU-based cores, you can see that they are in the uh, they can leverage a huge amount of computations. Next slide, please. Okay. Even it's not only about the technologies in the chips, but also each of the company has initially started with their own set of frameworks to promote, like Google promoting the TensorFlows, and then Microsoft also tried to put with the help of the FPGAs, even and then of course Meta, OpenAI, and so on and so forth. Some of them, they remain very much specific to the companies, and they have not come to the general purpose because there are multiple reasons for that. uh, because really making a chip and producing and releasing it to the large scale as a general has its own set of limitations in multiple ways, right? Probably we can deal later. Next slide, please. Next slide, please. Next slide. Okay. One of the things, whatever that is happening on at this moment, that could actually make difference to the HPC is nothing but the is nothing but the whether it's a monolithic or the wafer scale. Wafer tech is really a new technology. Now most of the chips up to now are monolithic, which essentially it meant that is that if you look at a motherboard, you can see a slot for the CPU, and then different set of slots for the GPUs and then TPUs. and then you have other slots for the Bluetooth, Wi-Fi connectivity, and so on and so forth, right? Now this is a monolithic, whereby essentially we are seeing different subsystems being integrated with the help of the bus, and they're connected, right? Now this poses a certain kind of limitations in terms of the data communications between the different subsystems, right? And then of course it will have implications on the in the computations, right? Now one of the things, it was nobody has verified it, but it was widely publicized. It is nothing but DeepSeek was actually deployed on a wafer scale systems, which essentially nothing but all these subsystems are put into a same single chip, right? And then they are like a 3D printed. So essentially what would happen is nothing but essentially the communication between different subsystems is drastically reduced, which also meant that the power consumption, the bottlenecks that would happen on between the communications between the different subsystems would also greatly reduce, right? So this is what the kind of trends that is going to happen on, saying that this is not going to be so easy, right? We see that the wafer tech is really so beneficial and looks so beautiful to hear, but it's not a mature technology, right? Now uh, probably anyone who has a bit of understanding of the semiconductor devices, they would know that the initially for example, if you look at the Intel nowadays, it's in news for not so good reasons, right? And then if you look into the fab sectors and then in manufacturing of the semiconductor devices, there are very, very small handy companies that are actually doing this, right? And then whatever that was top in few years, but like for example, if you look at AMD or Intel, right now they are not in uh, such a great position, right? But right now NVIDIA is in good shape, TSMC or many other, right? So one of the main reasons is that this producing the semiconductor devices, right? It's highly research oriented, and then in terms of the qualitative aspect of it, right? It's highly intensive in terms of the way it produces any kind of anomaly, even to a small micro degree itself also has implication to the whole batch, right? The previous slides, please. Okay. Yeah. Previous slide, please. Yeah, yeah. That's right. That's great. So essentially, what we are going to see is nothing but now one aspect of the high power computing, if it has to evolve, it meant that from the hardware perspective, if it has to improvise on this, this is one area that people would be looking forward. Apart from miniaturizing it to nowadays, probably we are speaking about 6 nanometer, 5 nanometer, or 4 nanometers, further reducing to 3 nanometers, that is happening on. So apart from that, what we can see is nothing but putting everything on the same single on chip, right? This is one trend that we are going to see, and it will have a very drastic impact on the system. So essentially what would happen is that these systems would become highly energy efficient, and unlike in the traditional systems where there is an impact on the bottlenecks, on the interconnectivity and limitations of different subsystems to connect, right? This will, because the communications between different subsystems will greatly gets reduced, and then in terms of scalability also, it will have a very good I mean, it will not be restricted by devices as such, right? And then of course it will have a certain impact on the heat management, which essentially meant that how all these chips which subsystems are going to be put on a single single chip, right? Will be managed, what kind of cooling systems will be applied, right? As such, now this is not a commercialized versions that have come at, and then I think this will take few more years to become a mature technology. Next slide, please. Okay, next slide, please. Okay, next slide, please. Okay, now I think what we have tried to understand is nothing but how this hardware is organized into different kinds of chipsets, and then what are the different kinds of types of chipsets that are getting available, right? More specialized. machine learning or for the AI or for the general purpose as such. But in terms of the performance, I think these concepts have remained very much stable for the last 20 to 30 years, right? In terms of the instruction sets, just to look at what kind of available parallelisms we can see. Instruction level parallelism, that which is something which will be supported by the specific hardware along with the compilers. And then we have wide varieties of chipsets, of course, and many kind of architectures in this. And then shared memory, or a memory for each one of them, that is part and parcel of this architectures. And then we have distributed memory systems where multiple systems are deployed and each one of them interconnected with network, right? And then specialized GPUs, right? Taking the weight of the computations, for the graphics related, right? And then FPGAs and specific application specific ICs, right? So yeah, these are the some of these things we have discussed, right? And then we'll see at more level on the software and execution aspect, right, as we go down. Yeah, next slide please. Yeah, previous slide please. Okay, I think this is implicit that when we speak of parallel computing, it's a parallel processing and distributed computing. This is all well and good. Now, when we look at systems, right, essentially what we are looking is nothing but a computational, on a single chip. We are looking at different cores, and each core has a ability to actually run some computation depending upon the instructions set. And then each one of them is associated with some sort of memory, right, which is accessible across different kinds of cores, or it's actually very much individualistic, right? Now, this will have implication on the performance of the system and also the architecture that we are going to use on, right? So we'll see some of these basics, but just to put differentiate, right? Now, what we execute, anyone who is aware of, primarily I come from C++ comp, right? And then essentially what we see is nothing but a parallelism that would happen on at task level. Now, in terms of the hardware level, it's much finer. Essentially, what we execute at the top level would finally get down to the hardware level. But saying that, I think as a HPC, once you are saying about the CUDA or the OpenMP, we are speaking at much finer levels, which are going to happen at the hardware level. And in the most recent trends, C++ and many other languages are actually in the process of ingesting these standards. Probably could have come in the 1990s, and then OpenMP is also in the 1990s. If you look at C++ compiler or .NET Award, I mean, in the most recent .NET standardizations and so forth, these are the ones which started really evolving post 2010, right? And in one sense, actually, it is driven by the ability of the computational capability of the available hardware and the kind of instructions that is possible with them, right? Okay, what you are seeing is nothing but a typical deployment infrastructure of any industrial system, right? Now, essentially, what you would see is nothing but bunch of servers for the application purpose. And then if we if we put into analogous to industrial systems, we can see different kinds of control systems organized at the ground level, or on the wayside, whereby they feed off through a proper networking systems, and essentially we have a very intricate set of L2 different kinds of routers and switches in between. And essentially all the information, it depends upon whether it is SCADAs or whether it is a there are different kinds of SCADAs. Okay, now we can see essentially all this information being actually pushed down from the ground systems to the servers, which align themselves to certain standards. And then these are the information is actually processed, and either the raw information or the processed information actually is put into the uh, backup systems. Backup systems or the either as a part of the yeah. So this is a typical components of a cluster in industrial deployment. In one sense, if we move into the scenarios whereby when we say as a cluster, we can say in terms of the HPC there are groups of nodes which are organized. Uh, in case of purely, if you look at data centers whereby the aggregations of hundreds and thousands of servers, right? It could be a different way of deployment. Yeah. Next slide, please. Next slide, please. Okay, coming back to the principal components of the any kind of supercomputers, essentially the processors, the aspect of it, and the memory aspect of it. And of course, once we have these processors and memory, and then we need to have the interconnection between different subsystems, and then more specialized accelerators. Example is a DPU that we have mentioned before, right? And then we have the storage subsystems, and then this storage is has a needs to support, right? And then there are different kinds of hardwares uh, hardwares and file systems that actually aid in terms of executions of this. And of course, for building up all these kind of systems, we have the operating system, compilers, and then different sort of frameworks, right? For parallel processing. And then for debugging and diagnostics, we have a separate set of software. So all these systems come together to one individual supercomputers. This may be a traditional way of putting every of the systems, every of the putting different kinds of hardware systems onto aggregated together in one place as a single entity. Or it might so happen that these are actually part of a grid system whereby we have a different kind of individual subsystems and each one of them connected and executed, right, in a distributed processing. Or nowadays, I think after the advent of the cloud computing, once again it's a different volume together. Next slide, please. When we are speaking about any deployment units, is either as a part of the industrial systems or as a part of the supercomputers, we generally tend to have a LRUs, which are nothing but line replaceable units, where each one of the system which you see is nothing but just like a what do you call plug in and plug, right? Each one of them part would be able to put them pull out and pull them back, right? Uh, this yeah. Now, this is a traditional motherboard, what we see on, whereby we see a motherboard with two CPUs, and then onto the right, what you see as a white is nothing but a PCI extension, whereby we can put uh, GPUs, TPUs, or any other processing that would come on. Onto the left, what you see is nothing but a pluggable RAM slots, right? And then we have the interconnection slots and so on and so forth, right? This is a traditional motherboard, and that's what is also there. Yeah. Next slide, please. Okay, now getting into the more niche subjects of this, more in terms of the architecture. Okay, what do we see? At the top level, we see only the application program, right? Now, uh, in terms of the HVC, once what we are seeing is not able to leverage huge amount of or deploying a certain kind of, let's say, weather modeling, right? We see an application which should be able to leverage a huge amount of computation down the layers. So it, which essentially is the one in the down, we can see that is the one which actually in the further level to the operating system, right? Whereby the operating system in lines with the hardware that is available, right? In terms of different kinds of instruction sets and the macro architectures, which is a combination of both the hardware and also the assemblers, which is supporting to it, which would actually run on the different execution units. Each of the execution is more analogous to a core execution on a single core, whether how much, whether it is able to, yeah. Next one, please. So what we see in this is nothing but we see application which is being deployed with which supports in multi-core and multiprocessor. Now this supported by the hardware can have an instruction set supporting with SIMD or MIMD. Now as to the instruction set architecture, which is further executed at the execution level, we can see pipelining of instructions happening at the execution units. Okay, now, yeah, before we go further, anybody has any uh, any questions or anything, drop me a message if there is anything, right? I can actually look into it. Now what okay, now as we go for, what we see is nothing but the instruction set is based on the in the architectures. We can see SIMD and MIMD, which essentially meant SIMD is meant for the single instruction and multiple data, and MIMD is nothing but multiple instructions and multiple data. So what exactly does it mean, and how is this able to leverage the computational capability of whatever that we are speaking on, right? And then we are speaking of high power computing, and then which essentially meant that ability to execute on the same system or on the different systems, or on the wide varieties of distributed systems across the different areas, right? Now this more or less in one sense translates to these instructions for acceleration, right? Which essentially meant that if I'm looking at a one single execution unit, I'm asking the system to execute once with a one single instruction, and then ability to execute multiple data, to compute multiple data at the same time, right? This is SIMD. And then when I'm speaking of MIMD, I'm actually saying that there are multiple instructions that are possible and multiple data to be addressed for each of the operations in parallel. Now, I think if anybody has a uh, anyone has a understanding of they have done some let's say before 2010s, if anybody has done any C++ programming, or let's say up to 2011 or 2013 or earlier before, right? They would see that the execution is always in sequential, right? But if you look at the standards which have come post 2011, most probably with of course the compilers ingested probably at 2013 or 2015 and later onwards, right? We can see with a single compiler instruction, or with a single, for example, I can say for each, right? In C++, or for .NET, or probably I think it's analogous to Java as well, right? Now these things would give me one single computational value. That is nothing but if I want to add 10 different, uh, uh, let's say each I have two arrays, each one of them is size 10, right? And then if I want to do an execution addition of array of A0 to B0, A1 to B1 as such, right? Now it's a one single instruction that would be fit enough for it to actually do it. But in principle, if it is much before 2012 or 2013, before the advent of C++11 or later standards, this would happen. This would happen. This would happen sequentially for each one of them, which essentially means nothing but 10 instructions, right? Saying that is the SIMD not available before? The architectures of SIMD, MIMD were always available. Left chain. No problem. So essentially they were available before, but they were not so much available for usage, right? In terms of compiler support. Now, if you look for the same thing, for example, if somebody who is developing a gaming or using the CUDA language, or who were more specialized into developing of the OpenMP, using the OpenMP and building the applications, they were able to leverage it, right? And not in the traditional programming of available uh, programming languages and frameworks. But this eventually changed later on from 2012 onwards, and we can see many of the compilers and frameworks are able to leverage it. Uh, okay, the previous one, please. Previous slide, please. Okay, previous one, please. Okay, what we are seeing here, is nothing but when we say of pipeline executions. Now, essentially, what we have is nothing but uh, execution units, and then okay, what we have is nothing but a instruction set, and then which is being executed by the core or the CPU. And then of course this is associated with the memory or the cache, and then any kind of instruction set at that point of time would actually go for the execution unit. Now in traditional, what we could see is nothing but the down, actually we can see two multiple execution units, right? This is execution of two instructions per clock. For the same single clock, we are able to execute two instructions, right? Which essentially meant that two operations are being performed simultaneously at the same time instead of one single operation. So what it meant is nothing but, if I want to, let's say, if as a graphics, if I have a bunch of pixels, and then on the screen which I want to print them, let's say out of 1 million, I nearly have 5 million pixels that can be updated with the same color for Samsung, right? And then all of them can be parallelized for updation. And then this is a kind of operations that would actually happen in a just a blink of an eye, right? And then this is all courtesy of the SIMD, right? So that multiple data, one single instructions to execute on the multiple data sets. This would if you look at current CPUs and GPUs, these are SIMD is widely being used, right? Next slide, please. Okay, essentially what is in a nutshell, all this is happening because of the extended register support that is that was available at the to do these operations, right? Next step, please. uh, yeah, These were actually introduced by the Intel and AMD in the x86 architecture. And then there is a support of 32 double precisions or 64 single precision floating point operations. And it's possible for 8 64-bit and 16 32-bit single operations to be done in parallel. Of course, all these things would have a deep implication to the domains and sectors that we discussed earlier, and then of course on the scientific simulations and artificial intelligence, deep learning, and audio video processing, and so on and so forth. Next slide. Yeah, okay. What we see here is nothing but a instructions and data, right? And then essentially what we are seeing is nothing but on the top, what we can see is nothing but one instruction and one data set. And then this is resulting, let's say if I want to add two arrays, more or less what we discussed, that we have a plus 0 plus b0, which is resulting c0. We are actually doing three instructions, and each instruction is supplemented with the data. So three executions. Now on to the right, what you can see is nothing but one single instruction and three data sets. And then this is resulting in one single instructions and three data executions at the same time. So instead of three iterations, we are seeing only one instruction causing the three executions, right? Which essentially meant that the efficiency is increased by threefold, right? So this is what the SIMD is meant for. Okay, next one, please. Now, yeah, next one, please. Okay, now what we have seen SIMD is on a single core and the ability to execute. Now we have multiple cores, and then each multiple cores, we have multiple cores, or the way the memory is supported in this is there is one set of specific memory associated with each of the core, and there is one common memory that would be associated with multiple cores together, right? Uh, and then there is one more amount of memory that would actually coordinate with the input output set of operations. Now, for us to actually do the parallelism, uh, okay, in the next slide, please. Yeah, perfect. Now, essentially, that's right. So essentially, what we can see is nothing but L1 cache, right? And then we have the L2 cache, and of course, uh, so any kind of operations or SIMD instructions that will happen on can be done for each one of the cores. And then in case if the multi-cores to be executed, it meant that each of the cores has to coordinate themselves. And then of course, the L2 cache would be used. The L2 cache would become a common cache, and then there is some synchronization mechanism that will come between the execution of core 1 and core 2. Apart from their SMD instruction set. Yes. Next one, please. Okay. Now what we can see is nothing but dual core, dual socket motherboard in a node. And then next one, please. Next one, please. Now, I think now for let's take a small example of saying that if I want to update some bunch of, let's say, 500 million pixels. Now, in a sequential way, if I want to keep on doing it without the GPU, it meant that the system would never be able to actually do it. Now, after the advent of GPUs, and then primarily for the graphics, supporting 1000 to 5000 cores. Each of the cores would be able to execute on their own pace to do the SIMD operations, which essentially meant that the time has drastically reduced. And then when I take into combination of SIMD or MIMD for executing on the which is in a way parallel executions across the clusters or distributed computing. Now the amount of calculations that would take would be very minute. Of course, which essentially meant that I would be able to do the computations for the much larger tasks. Next slide, please. Now, each of the HPC system, unlike a traditional general systems which are available on the shelf, each one of them has its own set of signatures. And then each one of them, it's not like there is a one standard architecture that would be used across. Each one of them, when it is built, is a combination of different hardwares, a different set of hardwares, and then uh, each of the operating system, combination of the hardware and then operating systems, and the compilers available at that point of time. And then, of course, one thing that could be said of uses of the open source softwares, something like Apache set of softwares, or from the open source foundations. So they have always aided in terms of the future technologies, and then they are also being used. One of in couple of organizations, I could see that open source Red Stack, I mean, based systems have been built, uh, but they are for a small scales. Next slide, please. Uh, well, ideally, it might so happen that each of the processes deployed would be scheduled, would be organized on the depend on the need of the application. But ideally, the ideal way is that all of them would be leveraged. Right? Practically, it would be much different. Of course, the efficiency of the system would pitch in at that point of time. Yep. Next slide, please. Uh, yeah, I think there are different kinds of all the algorithms that would come into the picture as a part of the whether their execution is done in the parallel, or whether it is using a divide and conquer or pipeline or domain decomposition, so on and so forth. Essentially, all this is nothing but translating the main problem into small subset of problems, and then executing them on the systems, right? And in one sense, all these things are more or less are the same kind of patterns that we can see being supported in each of the programming languages. Next one, please. I think these are very much widely known, so nothing much to delve into it. Next one, please. Next one, please. Yep, the previous one.
I have 5 minutes more.
Okay. Okay. So, what distincts from a specific system is in terms of its ability to execute concurrently, right? And then ability to scale it up, right? And then of course decomposing the complexes into smaller components or the smaller set of problems as such, right? These are the desirable attributes. And of course, there are some other factors that would also come into the picture. And then amount of computational capability it can support, amount of peak performance it can do, and then amount of power consumption minimized in a way, right? So all these things would come into the picture in deciding that. Okay, next one, please. Okay. Okay. Next slide, please. Okay. There have been good amount of standards that have gone in terms of building this parallel programming, right? Now, OpenMP and MPA is widely known. I have never seen this OpenACC. CUDA is also being used widely, right? Now, in the though these are the specialized set of skills that you would not find way too many, but these are widely known, right? Next one, please. So, of course, parallelism is a fundamental technique of HPC. Scaling up of performance needs appropriate communication networks and software stacks, which essentially meant that it's not only computation but interchange of information between different computing components, which essentially meant that the networks have to support and they have to be timed appropriately. Increasing the number of CPUs was a traditional method, but it has its own set of limitations, and that's where we have seen that CPUs, DPUs, and different kinds of specialized chipsets have come into picture. And then we can see the number of cores of each of the CPU getting incrementally going on, right? And also the algorithms for combining these frameworks are also coming to the picture, right? Now, just next slide, please. Now, what we can see is nothing but as an observer, as an interest in the C++, right? C++ is one of the languages. It was so beautiful, and then it looked like it stagnated up to 2009 and so on and so forth. But interestingly, from 11 onwards, what we can see is nothing but tremendous set of standards ingested from different kinds of domains and also from different different necessities of distributed computing. They're also getting ingested right now. It is in C++ 22 and 25, where we can see many of the specifications from the OpenMP are also taken in. They may not be in par with OpenMP. It's not like a complete alternative, but this is going in the direction of it. Next one, please. There is one more slide in between. Okay. Now, people who hasn't seen the CUDA or the OpenMP, you can just imagine it to be a bunch of compiler directives in the C++ code, whereby each one of them would give in case of CUDA, where we can specify which memory location to which memory location, which processor in a fine-grained way. Now, OpenMP is more or less in the same way we can envisage them. Yeah, I think this is almost end of my discussion presentation from my side. Yep.
Okay. Okay. Thank you very much. Thank you very much, Mr. Raghava. Excellent session on overall parallel computing architecture from the basics to as per your industrial expertise. Thank you very much. Audience, please ask any queries if you have. I think I didn't find out any query in the chat box regarding this parallel processing of HPC architecture or AI tools. Please directly ask the resource person, Mr. Raghava sir, for your queries.
I sincerely hope I haven't wasted your time. For me, most of this comes from whatever I have seen from the last 2 decades. It may not be much into your academic discussions, but this is very much based on the kind of industrial trends over a period of time. Yeah. If anybody has any quick questions, feel free.
I think the important slide is that sector feels current and evolving dynamics. I think everyone, hopefully you get this PPT, right? Maybe again go through that one. That's very interesting, and I see it's very informative also.
I'll just add a couple of points in this regard. Now, people has a understanding. People say that okay, as in more and more AI and neural networks and all these things comes into picture, it's possible that it have implications on the jobs and so on and so forth, right? It may be evident to whatever that is being traditionally being done, where there is a expertise that would be required professionally, but there is no creative aspect of it. But as we see, the problems are actually also getting more and more complex, right? And every time we reach to one problem, we'll have a new set of problems that will come into the picture, or we'll see much wider set of topics aggregating themselves towards into it and creating new set of problems, right? So in a sense that all this machine learning, data analytics, and then computing will aid us to create more and more set of problems and more set of jobs, right? It might so happen that in 1980s and 90s, accounting or having mathematics uh, brilliantly could be